Hi everyone. In today's lecture, we will discuss about diode models, that is models for diodes when analyzing diode based circuits. So before we go into the lecture, I just wanted to show a picture of one of the oldest diodes which were used in radio receivers. So they were mainly used for demodulating AM signals. Now here you can see that there is a metal wire and another material which is placed here. In fact, the material here, it turns out this was one of the earliest diode structures. Essentially, when I say diode, it's a two-terminal device where current can flow in only one direction. Now these were called as the cat whisker diodes because it had a very small, very thin metal, the shown here, made a point contact with a mineral which is shown here. So this structure actually permitted current flow in only one direction, and that was actually useful in demodulating amplitude modulated signals. Okay, so I just wanted to discuss this. If time permits, I'll see. I give a history of any topic that I teach, but if time permits, I'll try to present a history of the diodes, how they evolved from the late 1800s to early 1900s, then to what we have in today's times. Okay, so now we'll move on to the actual lecture, which is to develop models for diodes when analyzing diode-based circuits. We know that a diode and for a diode, the current voltage relationship is given by this equation here, where they have an exponentially, they both current and voltage, where current is actually exponential of voltage. It has an exponential dependence on voltage. So here, in an actual diode equation which was actually derived by Shockley, there was other parameter called eta, okay, which was called the ideality factor, and eta here for silicon it is 2 and for germanium it is 1, but for normal analysis we'll assume eta as 1. In fact, there is something called the ideal diode equation, which is the derivation for this equation. When we derive this equation, we make certain assumptions, and those assumptions are generally called as the ideal diode assumptions. So I'll just state one of the assumptions is that in a PN junction, when we derive these equations, we assume that in a PN junction you have the holes diffusing to the n side and the electrons diffusing from n side to the p side. We assume none of the carriers actually undergo recombination within the junction. That's one of the assumptions. Okay, before we arrive at this derivation, the final result, this is one of the assumptions we make, and under those ideal assumptions, eta doesn't figure in this equation. Okay, but when you actually assume that, there is recombination and all that, then we'll have to include a factor called eta, and it's called ideality factor. And for silicon, it turns out it is actually 2, and for germanium it is 1. Okay, so from this equation, as we increase voltage, higher and higher voltage, you know that the current actually follows an exponential path when the diode is forward biased. That is, when the voltage across the diode, which is this terminal here is the anode, this terminal here is the cathode, and is a negative seen as a negative terminal, current can always flow only from anode to cathode. Okay, that's why diode, it can only permit current flow in one direction. One of the simple differences between a diode and a switch, for example, switch is actually a 3-terminal device, but I'm just giving a comparison. A switch is a device in which current, once the switch is on, current can flow in either directions. Okay, current can flow in this direction or in this direction. It's a bidirectional device. Whereas a diode, a current can flow only in one direction. When it conducts only in one direction, and that it's called as when the diode is said to be in forward biased mode. Okay. Now the other direction, when you apply a negative voltage across the diode, when the voltage is negative, what happens is that the current ideally should be 0, but from this equation we can see when the voltage is negative, e power v upon vt for negative values of v becomes very small, and eventually it goes to very close to 0. Okay, so when this goes to 0, the result for current reduces to minus is. So eventually you get a current of value equal to is in the reverse direction. So that will flow from the cathode to the anode, which will actually flow in this direction. Is will be flowing in this direction. Okay, now this current is called reverse saturation current, and in fact when you see the derivation of a diode, the diode current equation, is has actually a dependence upon it actually is proportional to the minority carrier concentrations. which again is proportional to the square of the intrinsic carrier concentrations. Okay, so it has a very strong dependence on temperature. So if we change the temperature, IS will increase exponentially. Okay, to see the dependence, we will just solve one very simple problem. Okay, shown here. So here I'll assume that a constant current I is flowing through. I'll assume I naught flowing through a diode. Now you are supposed to find what is the voltage across the diode as temperature changes. Now we know that the expression for the current in a diode is given by this exponential equation. From this we can compute the voltage across the diode as Vt ln I by Is plus 1. Now Vt here is called the thermal voltage. It is 25.9, approximately 25.9 millivolts at 300 Kelvin. For any other temperature, you can simply find out using this relation, because Vt is just directly proportional to temperature. So for any other temperature, you can just use this equation to find Vt. Now the voltage across this diode is actually given by Vt ln I by Is plus 1. Now from this equation, it shows that if I naught, this is I naught here. So from this equation, if say I constantly gradually increase the temperature, then what should happen to the voltage V? So here I naught is assumed to be constant. It's a constant current source, is independent of temperature. Now as you increase as you increase temperature, we know that Vt has a linear dependence on temperature. So we should expect Vt to increase. It increases. So logically you would think that if you ignore Is, it will just, the voltage across the diode should also increase linearly. But since Is is also present, in fact Is has an exponential dependence on temperature. Okay, it has an exponential dependence on temperature. So any fundamental course on device physics will tell you that it has an exponential dependence on temperature. So what actually happens is that if your current is constant, your voltage starts reducing, and it actually reduces for silicon at the rate of 2.5 millivolts per degree centigrade. So if you, for every degree centigrade increase in temperature, the voltage reduces by 2.5 millivolts. Okay, so in fact this stems from the fact that your temperature, the reverse saturation current Is actually literally doubles for every 10 degrees increase in temperature. Okay, that is why it's a very, I'll tell you how does it have exponential dependence. For example, when you design integrated circuits, normally you design it for a temperature range of minus 40 degrees to 120 degrees centigrade. Okay, so which means the total range of temperature you design your circuit for is roughly 160 degrees. If you are designing your circuit for 160 degrees, okay, so which means as I said, if let's assume Is was the reverse saturation current at minus 40 degrees, at 120 degrees the value of Is will be Is into 2 power 16, because there is a totally, in steps of 10 degrees you have to reach 16 times. 16 into 10 is what you get. So eventually the Is value will be 2 power 16, so which is several orders of magnitude compared to the value at 40 degrees. Okay, so that is why reverse saturation current is a very important parameter. Normally what happens in integrated circuits is that sometimes you put diodes intentionally, sometimes diode structures are unintentionally formed. They are called parasitic diodes. They sometimes form unintentionally. So the leakage current of those diodes are a very critical parameter, because they have a huge temperature dependence. They can vary several orders of magnitude, and sometimes they can even affect the performance of your circuit. Okay. Yeah. So as I said, if time permits, I'll try to discuss about the dependence of reverse saturation current exactly on the parameters. Okay. But I felt, since this course is mainly focused on the circuits aspects of it, I don't know if I'll have if we will have time to discuss that. Okay, so we'll just come back to this problem here. So for silicon we can assume it is minus 2.5 millivolt per degree centigrade. Again, you can start from the device physics, fundamentals of device physics, and then show this result. Okay, at least a number very close to this. So the voltage actually decreases if your current is constant. Now your current is given by Is e power V by Vt minus 1. So from this equation, if this is the diode current, which is flowing in this direction, and the voltage is across this. So from this result, if let's say I fix the voltage, if I fix the voltage, then Is increases exponentially, Vt increases linearly. So this term is trying to reduce the current, but this term is trying to increase it. So eventually you will actually see an increase in the current. If you fix the voltage across the diode and then just raise the temperature of the diode, you will actually see a significant increase in the current, the DC current flowing through the diode itself. Okay, so that normally we show it on a graph. So if this is the curve for a certain temperature T1, if you increase the temperature, for the same voltage you should actually see a higher current. Okay, or for the same current you should see a lower voltage. The graph should satisfy both. Okay, so for the same current you should see a lower voltage. So this will be, the gap will be around minus 2.5 millivolt per degree centigrade, and this is for T2, where T2 is greater than T1. And in the reverse bias region, we already discussed the current is purely Is, which is the reverse saturation current Is. The current will actually increase significantly with temperature. It will have a large variation with temperature. So as increasing temperature, if temperature increases, the reverse saturation current also increases. Okay, so we have very briefly discussed about the temperature dependence of diodes and the current flowing through a diode. Okay, so with this I'll just discuss some few problems in diodes. So you are supposed to analyze these three circuits and find in this circuit you are supposed to find the voltage Vx at each node shown here in this circuit, here and here. Vx is this. Okay, all are assumed to be identical diodes. Okay, and I'll introduce a term called cut-in voltage very soon, and the cut-in voltage, the voltage required to forward bias a diode is much smaller than 5 volts in this example. Okay, so first we'll take the first simple circuit, which is just two diodes connected back to back. Okay, now since these two are identical diodes, and then you have connected a voltage source Vx, some V across them, and you are supposed to find the voltage across this diode. Okay, I'll call it V naught, even though I've shown it as Vx, it's actually V naught. Okay, output across this. Now if you look at the characteristic of a diode, now one thing you have to understand, this is actually 5 volts, it's given in the example as 5 volts. You need to understand that the diode actually, and here let me also make the assumption that the temperature is 300 Kelvin. Okay, so if your voltage is sufficiently large, then you can assume that your current is approximately equal to minus Is. Now when I say sufficiently large, what do I mean by that? If you look at the expression of the diode current, it is given by this. Now this result, e power V by Vt, will be much less than 1, or which will tend very close to 0 when your V by Vt is approximately is greater than minus 3 or so. We normally make it minus 3 to minus 5 Vt. So Vt here is 25 millivolts. So when I multiply it by 5, you would get approximately 125 millivolts. Okay, so when you have the reverse bias voltage less than 125 millivolts, okay, or when I say reverse bias voltage, it is the voltage across the diode. It's ideally, when you see it from in the graph, it will appear as a negative number here, but I can also show reverse bias voltage as a voltage like this, which is I can just use the anode as reference and cathode as the higher potential point. Okay, so in this case your reverse bias voltage can be seen as a positive number. If your reverse bias voltage is greater than 125 millivolts, which is almost 5 times Vt, this term it's e power 5, it's a large number. So 1 by e power 5, since it is negative, you will get 1 by e power 5, which will be very close to 0, or you can ignore, it will be much less than 1. Okay, so your current I will be approximately equal to minus Is. Okay, for V less than minus 5 Vt or even 3 Vt, we can make this assumption. Okay, Now since these two diodes are identical, those two diodes are identical, and there is a one-to-one mapping, we can say, because this is actually a one-to-one mapping current to voltage equation, because for each value of current there is only one value of voltage you can have from this result, and we are enforcing that the currents through both the diodes are same, because the reverse bias, both of them are same. Since they are same, then the voltages also have to be same. They are identical devices, so IS is same, temperature is also same, VT is same, so therefore the voltages also has to be same. So each diode will drop 2.5 volts across them, and the current drawn through the diode will be approximately IS, okay, because that is the maximum current it can draw. And as I said, if your voltage is greater than 125 millivolts at 300 Kelvin, then you can approximate the current to be equal to IS itself. Okay. The other circuit is where we connect a reverse biased and a forward biased diode in series. Now we'll have to find out what will be the voltage across this diode. I'm going to call this V0. Now you need to see that if current flows in this direction, then this diode has to be in reverse biased, this has to be reverse biased, this diode, and this diode has to be forward biased. Okay. Now we can see that the negative terminal of the diode, or the cathode of the diode, is actually connected to a positive voltage, so this diode has to be reverse biased and this has to be forward biased. Now we know that we discussed that if the diode is in reverse bias, and we know that when the diode is forward biased, it's going to the voltage drop across it, it's going to be very less, okay, because the current has an exponential relationship. The current actually has an exponential relationship with voltage, so the voltage drop is going to be very less. Even for small changes in the voltage, there will be drastic changes in the currents, okay. So I can assume that most of the voltage falls across the reverse bias diode, and we know that most of the voltage falls across it, the current is going to be minus IS. I mean, minus IS here is, the direction of the current is important, so you'll have a current IS flowing in this direction. Now all you need to do is to find what is the voltage corresponding to IS in this diode, because this diode is forward biased and a current IS is flowing through it. You need to find so you need to find IS is the current here, so what is the corresponding voltage? So we know the voltage is given by VT ln I by IS, so in this case I is IS plus 1, so you'd get VT ln 2, okay. Now if you look at this circuit, the voltage across the diode is actually just proportional to VT. It's directly proportional to VT, okay, and it is independent of IS, so it has only a linear dependence on temperature. So such a voltage is normally called PTAT, proportional to absolute temperature voltages, okay. There a very similar idea is used in generating constant current sources on analog integrated circuits, okay. So such voltages are called PTAT, or proportional to absolute temperature voltage sources. So let me give another problem. So wherein assume that you have a diode and you are forcing a constant current through a diode. These two are identical diodes, okay, and here I am forcing a current I, and here I am forcing a current N times I. Now we need to find the voltage difference between these two diodes, okay. And again I'll define one other important parameter, that the reverse saturation current usually will be of the order of 10 power minus 12, which is 1 picoampere, okay, and the normal operating currents would be of the order of few milliamperes to, it depends on the circuit, but I'm just giving a general number, it will be of the order of few milliamperes. So if you see, this ratio is pretty huge, okay. So we'll make this assumption and try to find the voltage. I'm going to call the voltage across the first diode as V1 and the second diode as V2. The output voltage is V1 minus V2. Now what is V1? V1 is VT ln I by IS, okay, plus 1 minus VT ln N times I by IS plus 1. Now since this ratio I upon IS is like 10 power 9. I mean, if I assume 1 milliampere of current, the ratio I by Is is very large. It's 10 power 9. So I can ignore 1. In comparison, I can actually ignore the term 1 here. So you get this result. And when you subtract the two, you would be left with Vt ln. You would have to divide this by this. You'll be left with 1 by n or minus Vt ln of n. Okay. So now if I actually take voltage between these two, wherein if I subtract V2 minus V1, I am going to get a Ptat that is proportional to absolute temperature. Okay. But now this voltage actually has a negative temperature coefficient, meaning if you increase the temperature, the voltage is going to reduce linearly. Okay. Such a voltage is called Ctat, complementary to absolute temperature, or is a negative Ntat, negative to, sorry, it's called Ctat, complementary to absolute temperature. Okay. It just reduces linearly. So if I just plot in the first problem which I discussed, the voltage would increase linearly. In this case, with temperature, the voltage across the diode. In this case, the voltage will decrease linearly with temperature. Okay. And in fact, I should show it properly because it's negative. So in fact, it starts from 0 Kelvin and then it reduces linearly like this. Okay. Here if you can just see, if I just interchange the polarity out, if I just take output as V0 as V2 minus V1, I will get a Ptat source which is Vt into ln n. I will actually get a positive temperature coefficient. Here if I just by just interchange in this problem, we actually get a negative temperature coefficient. Okay, so this way we can, if you can somehow generate a constant current source and then force it into a diode, you can actually generate and by doing some additional, by doing some extra manipulations in circuits, you can actually generate Ptat or Ctat voltages. Okay, so I'll go back to this problem which we discussed in the final problem here. That's a very interesting problem. So what we do is that in this problem is that you take n reverse biased diodes, connect them in parallel, and finally connect it through one forward biased diode, and you are supposed to find the voltage across this. Okay, here you have totally 1 to n diodes and everything is connected to a 5 volt source. Now when you look at this circuit, we know that all the reverse bias, since they are all in parallel, I can just treat them as a single diode with an area n times a. Okay, I can just treat them as a single diode with an area n times a, or even I can just assume they are all in parallel. Since all the diodes are in parallel and they are all reverse biased, all of them are going to carry a current of Is. And this current here is going to be sum of all those currents, which is n times Is. Okay, and that is going to be the same current which is going to flow through this diode, which is n times Is. So the voltage V0 is going to be Vt ln n plus 1. I've used an exact equation. It is Vt ln capital N here. I've assumed it is n plus 1. Okay, so again this is a Ptat source. The voltage actually increases linearly with temperature. Okay, so that's very briefly I wanted to discuss about the dependence of diode current equations. Okay, and how to generate Ptat and Ctat voltages using diodes. Okay, so now we will go about building the models for diodes. Okay, so first consider a very simple circuit where you have a diode and a resistor. When you apply a voltage, say an input voltage Vx, the voltage across the diode as V and V0 as the output voltage, and let's assume I is the current flowing in this direction. So when you have a circuit of this type, if I write KVL in this loop, I am going to get Vx equals V, which is the voltage across the diode, plus I into R. Okay, this is one equation we have. Here there are two unknowns, which is voltage and current. There are two unknowns in this equation. Now also the voltage across the diode, the current voltage across the current and voltage relationship for the diode is given by I e power V by Vt minus 1. Now to find the voltage and current in this circuit, I have to actually solve a nonlinear equation. Okay, because to find, there are two unknowns and there are two equations, but the other equation is a nonlinear equation. So you can't do a hand calculation. You can't simply solve this problem just by using simple hand calculations. Okay, you have to solve it iteratively or use a computer to solve it. So even if a simpler circuit, in a simple circuit, if you just add one diode to a diode based circuit, okay, it becomes extremely difficult to do hand calculations. So therefore we actually need to develop simple models which can be used to greatly simplify the analysis of diode circuits, wherein we can do hand calculations at the same time give us very accurate results. Okay, so that is the reason, motivation behind going for models for diodes. One of the simplest models of a diode, which is normally used for very low currents. Okay, so I'll for very low currents, it's called as the ideal diode model, is when you assume that the forward voltage of a diode is zero, meaning when the diode is conducting, you assume that it's like a short circuit. So by definition, a short circuit is nothing but the voltage is zero, but current can be anything. You can have a large current, so I'll have to show it in a different color. So you can have a very large current across it, but the diode voltage is zero. Okay, so when your voltage V is greater than zero, the characteristic is on the y-axis itself. So this is I versus V. Now when your voltage is less than zero, when your voltage is negative, you assume that the diode is an open circuit. So when a two-terminal device is open circuit, it can have any voltage across it, but the current will always be zero. So the characteristic should look like something like this. Okay, so this is the characteristic, IV characteristic of an ideal diode. So when you make this assumption, so this circuit reduces greatly. So if I assume Vx is greater than 0, if Vx is positive greater than 0, so all you need to look for is this terminal greater than this? So then the diode will be just replaced by a short circuit. So you can just, it's a short and a resistor Vx is connected. So you will have your current flowing, this is simply given by Vx by R. So it's a very simple circuit, you can very easily solve it. And this is valid normally for very low currents, currents less in the order of microamperes. Okay. And again, if Vx is less than 0, we can simply assume it's an open circuit, the output also will be 0 in the same circuit. Okay, if I assume Vx is less than 0, the diode will be reverse biased and it's an open circuit. So again, here the point to keep in mind is that by definition, if I ask you to draw the IV characteristics of a short circuit element, where an element is short circuit, you can have any current through the diode, but any current through the element, but the voltage should be 0. So it will be the entire y-axis. Okay. Similarly, for an open circuit, it will be the entire x-axis. Okay, it will be the entire x-axis and entire y. This is for short circuit, this is for open circuit element. If I say an element, you open circuited two nodes, it means that the voltage can be anything between the two nodes, but the current is always 0. Similarly, if I short circuit two nodes, the voltage across the two nodes is going to be 0 and the current can be anything. Okay, that's the entire y-axis here. But since a diode is a unidirectional element, it can carry current only in one direction. So I have to simply consider only one direction. So this is the voltage is along this axis and current is along this axis. When it's forward biased, your current can only flow in this direction, and when you're reverse biased, current can again, voltage can be only negative across the diodes. Voltage cannot be positive. Okay, in that case you can't assume it as an open circuit. Okay, so yeah, that's the basic definition here. So in this model, it's the ideal diode model. It's called as the ideal diode model. So when the diode is conducting, meaning when the diode is carrying current, it doesn't dissipate any power. It literally dissipates 0 power because the voltage across it is 0, even though the current is finite. Okay, so the power dissipated by the diode is 0 if you use an ideal diode model, and this is valid for very low currents of the order of microamperes. Now what we will do is we'll just analyze the diode current equation a little bit to get an idea about what will generally be the forward drop voltages of a diode. So we know the diode voltage is given by Vt ln I upon Is plus 1. So I'll take some practical numbers. I'll assume that Is is around a picoampere, which is 10 power minus 12 amperes, and we'll start with a current of 100 microamperes, which is 0.1 milliamperes. For that, if you substitute this and find the value at 300 Kelvin, you will get a value of around 0.47 volts. okay, or 0.477 volts. Now if I make 1 milliampere, I am going to get around 0.536, and 10 milliampere, it's going to be 0.596, it is close to 0.6, and 100 milliampere, it's going to be 0.656, and an ampere you are going to get 0.7156. Now if you look at these numbers, even though I am changing the current by a factor of 10, the change in the voltage is not that significant. Okay, that's purely, it comes from the exponential dependence. Okay, so even if you are changing your current by several orders of magnitude, you are taking ln of that. And logarithmic function, I said in one of the previous lectures, it acts like a compressive function. It, even if there is large changes, it won't get reflected when you take logarithm of it. So normally what we do is, if your current is in the order of few milliamperes, we just look at this range of currents where you operate, and then we can say roughly a voltage of 0.5 volts. So when you draw the IV characteristics, okay, we can say that here I am going to use a word called cut-in voltage. Okay, it's like a threshold voltage for a diode, meaning if your diode voltage is greater than this, then it conducts. Instead of saying, in the previous model we said if your voltage is positive, we are saying it's conducting. But in this example, I am going to say that if the diode voltage is greater than a certain threshold voltage, okay, and I am going to call it as that cut-in voltage. So normally how do you find cut-in voltages? First you see the range of operation of your diode, and then plot an IV characteristics within that range. So I max to I min, okay, and then extrapolate this line because it's exponentially increasing. In fact, the graph would simply look like this. Since it's exponentially increasing, you can just extrapolate this line and see where it cuts the x-axis, and we'll call it as V gamma, and that will be your cut-in voltage. Okay, so I've given a voltage drops across the diode for different values of currents. Normally when you go for low currents, the order of milliamperes, tens of milliamperes, you can approximate it to 0.5, 0.6 volts. So you can see here it's going towards almost close to 0.5 to 0.6. Okay, so V gamma is assumed to be 0.5 to 0.6. But if you are going for higher currents, in power circuits, then it might even go from 0.7 to 0.8 volts. Okay, so normally you would be seeing 0.7, 0.6. It also depends upon the value of IS. Okay, here I have shown for a value of IS as 10 power minus 12. So the typical values you would be seeing would be 0.7 to 0.7, 0.6 to 0.7. Okay, so this cut-in voltage is purely derived based on the circuit designer's convenience. Okay, you actually extrapolate it, you draw the I max and then I min, and then find the value of V gamma. From that becomes your cut-in voltage. Okay, but you should not confuse it with built-in potential. Built-in potential is very different. It's a fundamental parameter of a device. It's unchanging. It doesn't change with currents. Okay, it's a fundamental parameter of the diode itself. Okay, so cut-in voltage, on the other hand, it's more of a circuit designer's convenience. So we use it for analyzing circuits. So what you do is, now when you have a diode characteristic like this, you just approximate the diode as a device which will only conduct only if the voltage across it is greater than V gamma in the forward direction. The reverse direction, we assume again it doesn't conduct. There is no conduction in the reverse direction. So in this model, in the forward biased region, we are actually modeling the diode as a voltage source of value V gamma. Okay, normally when you show the diode including this, we assume an ideal diode, and then a voltage source is shown in series with it. Okay, so if this node voltage, if the voltage, so now this and this together represents the model of a diode. So naturally I am going to call this V1 and this node voltage as V2. If V1 is greater than V2, or if V1 minus V2 should be greater than V gamma for this diode to conduct. Okay, because this node voltage here is at V gamma volts. If I assume V2 is at ground, assume V2 is 0 volts, this node voltage is at V gamma, so for V1 has to be greater than V gamma for it to conduct. Okay, so this is the model for a diode with a finite cut-in voltage. And again, As I said, it depends upon the current range of operation. Based on that, V gamma can change. But the typical values for silicon diodes would be 0.6 to 0.7 volts. Now in this model, again, if you see this, now the model for the diode is this entire between these two terminals is entire. We put a diode in series with a voltage source. Okay. The reason why we put a diode is that this is just to show that the current can be permitted only in one direction. Okay. If you look at this, the ideally voltage source can actually take current even in this direction. Okay. But here the model shows that the current can be flowing only in one direction. Now as I said, it is in the first quadrant, so therefore power is absorbed by this element. Okay. Or I can say power is dissipated. So in this model, when I assume a finite cut-in voltage, you also capture the effect of power being dissipated across the diode. Okay. So we capture the effect of power being dissipated across the diode if I use a model with a finite V gamma. So I'll solve a few circuits assuming a final ideal diode. When I say ideal diode with a finite cut-in voltage, so first so in this circuit you are supposed to find the input output characteristics. You are supposed to find a graph. This is input and input versus output. So first we'll assume input is negative. If your input is negative, what happens is that current has to flow in this direction. Okay. So then the diode is, here I'll assume V gamma as the cut-in voltage. Okay. I just wanted to mention this. Now I'll just come back to the problem. In the reverse direction, the diode can be treated as an open circuit. So because the diode is an open circuit, the current flowing through the resistor is 0, right? Because it's an open circuit, there can be no current flowing through. I can just replace the diode by an open circuit, and V0 will simply be equal to Vi. So when your Vi is negative, your V0 will be equal to Vi. Now I will keep on increasing my Vi. Okay, I'll first analyze for two cases. When first we'll assume that Vi is 0, V gamma is 0, meaning a perfect ideal diode for small currents. Assume V gamma is 0. If V gamma is 0, then the instant your input voltage is greater than 0, okay, then this node voltage will be greater than this node voltage. The diode will start conducting and this will become a short circuit, and your output voltage will be simply 0. Okay, the output voltage will simply go to 0. If I assume a finite V gamma, where V gamma is finite, then until your input voltage reaches V gamma, your output is open circuit. Okay. After it reaches, when your input reaches V gamma, you can replace your diode with a voltage source of value V gamma. So in that case, the output voltage will always remain constant, whose value is V gamma. Okay. So meaning, if let's say for example your input is a sinusoid, I am feeding a sinusoidal input to the system, to the circuit, what you will get is that in the negative half cycle, the output of this circuit is going to be you are actually going to get I'll draw it in a different color. So you are actually going to get the same output, or you are going to get the same output when the output voltage is negative. But in the positive half cycle, when your output voltage reaches V gamma, it will flatten out like this. Such a circuit is called a clipper. So your output will look something like this. Okay. So this circuit is called a clipper, and this is one of the applications for the circuit, for a diode. Okay. Okay. So when you model this, when you use a model, you can actually show what will happen in the circuit. Again, as I said, you can predict the behavior of the circuit very accurately by going for such models. Now similarly, we will take another circuit where say I connect two diodes in parallel. So let's just analyze this circuit wherein you connect two diodes in parallel. Okay. Now in this circuit, let's assume I apply a positive voltage across across the two terminals. Then what would happen is that this diode will conduct. Assume they are diodes with a finite cut-in voltages. So when this voltage is greater, so I'm going to call this as V voltage across it. If it is greater than V gamma, the above diode is going to conduct. So you are actually going to get a graph. If I'm going to plot the IV characteristics of this composite device, I'm going to get something like this. When your voltage is output voltage is, the voltage across the diode is going to be greater than V gamma, you'll have a current flowing through this. And similarly, when the voltage is less than V gamma, when the voltage is less than minus V gamma, okay, for any other voltage there will be no conduction, okay, because both the diodes will be off. When the voltage is less than V gamma, then this diode will conduct and this diode will not conduct. The current will flow in this direction. So I can say the current is negative when your voltage is less than minus V gamma, or voltage across it, you will have a current flow in this direction. Okay, so this is a bidirectional element, but then I have constructed it using two diodes. But again, if you notice this, current can flow in both the direction, and we are using voltage source models for the diodes, but still the composite device, the IV characteristics of the composite device still lies in the first and the third quadrants. So which means power is only dissipated across the diodes. Okay, it's an obvious fact, I'm just stating it again. So now using this, if you are asked to plot the IV the input output characteristics, output voltage versus the input voltage, then using the similar analysis, we can very easily show that when your input is between minus V gamma to plus V gamma, the current through this is 0. I can simply model the circuit as an open circuit. Both the diodes are open. Okay, so output will simply be equal to input, right? So because the current through the resistor is 0, the drop across this is 0, so your input will entirely appear across the two diodes. So in this range, you will actually have the input and output following each other. The gain is 1, Vi and V0. After this, your output will saturate to a value of V gamma, and in this it will saturate to a value of minus V gamma. Okay, so for this characteristics, if I feed an input sine wave which is going from minus V peak, some peak value, plus V peak to minus V peak, okay, now you need to find where does V gamma occur here. So this is V gamma, and this line is going to be minus V gamma. So you are actually going to have a graph which will look like this. Okay, so it clips in both the directions. It clips the waveform in both the directions. We will go much more detail when I'm analyzing different applications of diode circuits. Here I just wanted to show the effect of models. How do you predict the outputs very easily using the models. Now when you actually build a practical circuit using the diodes I showed in the figure in the previous example, let's say you build a circuit like this, you will actually observe a very small variation on top of this. It won't be a perfect, a straight line like this, but rather you would get a waveform like this. Okay, you would actually get a waveform. There will be a small variation here that you will notice. Okay, it will also be like a sinusoidal variation, but there will be a small variation. Okay, now why do you get that? So that we will try to analyze it. So now this diode model doesn't capture this small variation. Okay, so as we discussed, when we use a cut-in voltage model, what you essentially assume that, of course, it's going to make the analysis very simple. You can just use hand calculations. It's extremely simple to analyze circuits using the cut-in voltage model. But then it doesn't capture small effects. So for example, what you're actually doing is that it's an exponentially increasing curve, and you're modeling it with a curve like this. This is the modeling curve, and this is the actual curve, modeled curve. The curve used in modeling, and this is the actual curve. Now if you look at it, as your current increases, okay, the model is significantly going to diverge. You are always assuming the voltage is constant across it, but the voltage across the diode also increases when your current increases significantly. That is not captured in this model. So what you do is that As I said, again we have to use only linear circuit elements because it becomes difficult to solve nonlinear equations. That is the main purpose of going for models. So what we do is that we start adding a resistor to the model in series with the voltage source. So instead of just modeling it as a cut-in voltage alone, we will just model it with a resistor like this. Okay, such that the graph models the IV characteristics to a greater accuracy of a diode to a better accuracy. So in this case what you do is your diode in the forward bias region, since the reverse bias it's always simple, you can simply assume it as open circuit, it's done. All these models we are talking about is mostly in the forward bias direction. Okay, so in the forward bias direction you can model this as a diode with zero cut-in voltage diode which is in series with a voltage source and a resistor. I am going to call it as R on, the on resistance of the diode, and this as V gamma. Now how do you find R on? The value of R on can be found from the IV characteristics of a diode. Okay, so what we do is, when you study the analysis of amplifiers, you will know that most amplifiers have what we call as a bias point or a quiescent point, okay, around which you normally operate those amplifiers. So same way we can actually find a quiescent point for a diode around which you are going to operate this diode. In this region the model is going to be accurate. Okay, you can approximate it as a straight line in this region. As I said, it's only an approximation. In this region we are going to find this. So all you need to do is find the slope of the curve in this region. So di by dv, and inverse of it will be your R on. Okay, and again I is given by is e power v upon vt minus 1. So from this we can compute dou I by dou v as is e power v by vt into 1 by vt. So this would be is by vt into e power v by vt. Now this result I am going to call it as the quiescent current. So I diode quiescent by vt. Okay, this is the quiescent current at which we are estimating the resistance. So your R on will actually be I diode quiescent upon vt. Okay, so again the on resistance actually depends upon the current, but as I said, this model will be accurate when you are going to operate your device in this region. Okay, the error is within certain acceptable limits. So now we'll use this model and try to analyze this circuit. So if you look at this circuit, in that case the model for the two diodes like this, when I model the two diodes in series, the characteristics is now going to look something like this. Instead of two straight lines previously, now the characteristic is going to look something like this. Okay, this is the two actual characteristics with finite R on. Okay, both the slopes are positive here. Okay, and the inverse of this slope is 1 by R on. I should write it as 1 by R on. Okay, so now when the diode is conducting, as I said, in the two diodes only one of them conducts when your input is greater than V gamma. So when your input is greater than V gamma, only one of the diodes is going to conduct. So I can simply replace this as a voltage source V gamma and a resistance R on. Now in this model, as I said, your input is already greater than V gamma. Okay, the excess voltage will appear across R on. So I am going to draw the incremental model for the diode around V gamma. So your circuit is going to reduce something like this. So this is Vi. The voltage across output is going to be R on by R plus R on into Vi. Okay. So previously the output characteristic, when you connected two back-to-back diodes, we just discussed this problem. We had minus V gamma plus V gamma. The graph was linear in that range, and after that it saturated. Outputs were constant in the first model. Now when you include an R on, finite R on, the gain here is going to change. That's the only difference. Okay, initially the gain was 1. Now since R on will be much smaller than R normally, so the gain is going to be very small, so which is shown in this graph. Okay, so it's a different gain. So here the gain is 1, here the slope is R on by R plus R on. That's the main difference. Okay, which is why what happened is that when you fed a sine wave to this system to this circuit, in this range the input and output followed each other. Okay, now in this range when your input is greater than V gamma, in this range when input is greater than V gamma, the gain has changed, the gain has become very small. So even though there is a sine wave changing significantly here, you will actually get a small replicated version with a small gain here. Okay, so that it's essentially a sine shape with a small gain you will be seeing here. Okay, so here the gain is 1, so the input and output match exactly. In this region the gain is much small, so there is a gain discontinuity at this point. Okay, so instead of a flat line that we were expected to see in a regular model, this model captures that effect. Again, this is what you will be seeing in a practical circuit, and that can be captured by modeling a finite resistance across it. Okay, so this is the final model. I'll just cover one other thing which is done in a slightly advanced models for diodes. So as I said, a diode can be modeled using a finite resistance, okay, and with an on resistance of R on. Okay, now when you actually need to model it more accurately, now the diode characteristics, as I said, is an exponential characteristic, and the graph model which we have used is going to be like this when there is finite V gamma, and even if you assume a finite slope, it's going to be something like this. But now as you see here, the value is actually going to increase. The error between the actual curve and the model curve is going to increase exponentially as you increase the input voltage. Okay, so to reduce that, what we can do is we can actually build a better model. What we do normally is that to make a better model for it, you just need to design a system with a varying slope. Okay, all you need is a variable slope. So now this function is going to have a different model. So what I'll do is, I'll actually try to discuss about the models in more depth, the variable model, the models with a variable slope in the next lecture. Okay, I'll discuss this in the next lecture now. There is a small disturbance here. We'll discuss it later. Thank you.